Welcome to Study Guide for Midterm 2 for Computer Science 330/Physics 306. My name is Dr. Jordan Hansen. Let's begin with Chapter 6, Functions of Combinational Logic. In this problem, we're asked to design a circuit below that adds two numbers in binary corresponding to outputs from two separate encoders. So we can make a function block representing our 4-bit adder. Why do we say 4 bits? Because in part B, we're going to demonstrate how the design adds 1 and 9. So we only need 4 bits to describe such numbers. So let's do 1, 2, 3, 4 inputs right there. And we'll say A with a subscript I to represent the first 4-bit number. And we'll say 1, 2, 3, 4 input lines for our number B. So you can think of this first line as A0, A1, A2, A3, etc. So those are encoded binary numbers. And then the output will have 4 bits and a carry out. 1, 2, 3, 4, and then we'll say C out. Now, you can imagine, so in the circuit diagrams in the chapter, you can see that the number of sum bits in a full adder for a 4-bit full adder is equal to 4 plus carry out, and there's also carry in, which we're going to tie to ground. Let's see in. Now, you could put 15 and 15 and get 30, and that, of course, would require 5 bits to represent the number 30, but you do have 5 outputs. You have carry out and then 4 regular. So we can call this, for example, C. But remember, these are encoded by 2 encoders. So let's represent one encoder with 1, 2, 3, 4 lines, and we'll call this encoder 1. And then we have to have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll just say 1 through 9 lines into that encoder, which will contain the appropriate and or logic to change whatever key we press that activates these lines into the right binary. Now for the first one, because we're adding, then let's just connect these outputs to these inputs. Probably we're going to want to do active low, that kind of missed. We'll connect this output as well, like that. And so let's make this active low by putting little inverter symbols here. 1, 2, 3, 4, and then we would want to do active low on this side as well. That way, when you actually press a key, it goes from consuming no energy to consuming energy temporarily and then back. So this is your supply voltage, and this would be ground. And so as soon as you ground something, then there's a current that flows, et cetera, et cetera. That's a minor detail, and honestly, the logic could function active high or active low. Okay, now for the second inverter, I should say encoder with inverters on the outputs, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 through 9. We can just connect here like that. And then make these active low as well. And then we could press a key. So technically, we don't need a 0 key, because we could just assume if it's active high, then these inverters will spit out 0. So 0 and plus 0 is just automatically 0. But if we press something, then the adder will be forced to add, let's call this FA for full adder. If we press a key, then the adder will be forced to add whatever is spat out of either encoder. And that would accomplish the adding, But in the third part, it says add a separate input line with Xnor Gates that switches the system to subtraction in 2's complement form. And so we're going to have to make some changes. In particular, let's try to change just the bottom half of the circuit. And so the main thing with 2's complement, of course, to change a number to 2's complement, you have to both invert it and you have to add 1. So our C input line to the full adder will have to be modified. Let's put our subtraction switch over here. We'll just call it S. I want it to be active low, so we'll put a little invert right there. Or we could just say, yeah, I mean, it's active low, but that then just begs the question, what is the uh, use of the Xnor gate there? So if we recall, the truth table of Xnor is like a fundamental comparator. So if we have A and B and the output X, let's enumerate the states to get the truth table, 2, 3, like that. So 0, 1, 0, 1, 0, 0, and then 1, 1. That's a true, this is false, false. Now, we're going to want to put an inverter on Cn. So that, I think, will take care of the, let me just do this. That will take care of the 2's complement requiring that we add 1. But we also have to invert this binary number that comes out of the second encoder. And so we need some Xnor gates because if you, um, by the way, if this is active low, if this signal goes low, then this will be a high, and that's what I mean in order to get Cn to be +1. Now, the Xnor gates, notice that if this were to become like if this default state of this switch is just to spit out a 1, and then that inverter will change it to a 0, so it reverts back to the original behavior. But if the switch, its default behavior is to spit out a 1, let's call this the B input, and then A will be coming out of whatever, like the binary bits that are coming out of the second encoder. So if the default behavior is for the switch to spit out a 1 so that B is a high, then notice that A is equal to X here, and then A is also equal to X. In other words, uh, you know, A XNOR true equals A. But if you look at the other cases where if B is 0, then A comes in as a 0 and leaves as a 1. And if B again is a 0 here, if A comes as in a 1, then it leaves as a 0. So A XNOR false equals A bar, we can write. Now to get 2's complement form, you have to flip every bit and then add 1. And that's what we want. So we need these XNOR gates to accomplish that. And so we need this active low signal to do that for us. So if we have, let's say, an XNOR gate like that, then what we want is for this input to come in like that, and then we're going to peel off that voltage, and then this goes in there. And then we can do a second XNOR gate, connect there. This input comes in here. I need to put my little dots to indicate a connection. And then we have that. And then same story twice more. So I get my third input like that. So now we have 4 Xnor gates that are responsible for flipping the bit stream that comes out of this second encoder, provided this active low switch will do that in cooperation with the second encoder, and then the active low will then become active high here for the CN plus one. So this is an add subtract with 2 encoders. Now we move on to the second problem of chapter 6, function of combinational logic. Using basic logic gates like Xnor and inverters, create a comparator that yields high if the magnitude of two 2-bit binary numbers is equal. Assume that one or both of the numbers is a negative 1, and that if a number is negative, it is in 1's complement form. Now, before we begin drawing circuits, it's important to understand all possible cases that we're going to have. So if we have A and it's a positive number, and then also B, and that's a positive number, we just have to do a standard comparator. We also have to account for the case where A could be, a negative version of itself. Let's just say it's some number that's negative, so I'll just say bar to represent that um, qualitatively. And B could be a positive number, and so that we'd have to have, a second kind of comparator. So there's going to be comparator 1 for this case, and then comparator 2 for that case. But keep in mind, so if these are equal, and obviously we're thinking about the magnitude, so if A is a negative number, but it has an equal magnitude to B, if you took if you took the inversion of both sides, however you say that, the negative or the complement of both sides, then A would be equal to B bar magnitude. And so that also would be comparator 2. So I think it's sufficient to say make comparator 2 and comparator 1 and then OR them. So there's two different cases. If they're both positive, then you get one kind of comparator, and if they're both negative, then that's also comparator 1, right? Because then you could just take the complement of both sides and then take the magnitude, and that would be comparator 1, because you'd recover A equals B. So the point is, there should be one kind of comparator and then another kind of comparator, and they correspond to same sign and different sign respectively. So uh, how do you handle making a single comparator from gates? Let's try that. Well, if you have 1 bit, then the Xnor gate is what you need. So if you have A and B, what comes out is if A equals B. And so to modify that for 2-bit binary numbers, what we have to do is say, okay, well, here's the least significant bit, so A0, B0, and then A1, B1. And then if we AND those, that means that all bits are equal. So the A0 equals B0 and A1 equals B1. So this is for this output X corresponds to our first comparator. Now we have to construct a comparator that will ensure that the magnitude of A and B, two 2-bit binary numbers, is equal if one of them is in 1's complement form. So the way that we can do this is to make the same comparator with 2 Xnor gates, but then we should flip the bits of one of the binary numbers. So we're going to flip A0 and A1, assuming that they're in 1's complement form, and then B0 and B1 would remain unflipped. And it would be the same circuit. The labels A and B don't matter. If we flipped the wrong number and they had the same magnitude, they would still have equal magnitude. Like if the, -1 is equal to -1 or 1 is equal to 1, if you flip them to positive or flip them to negative, they're still having equal magnitude. So then we have an AND gate here, and that would be our output. And so then I think we would want to OR these two comparators. So to start the main circuit, we're going to want to work backwards from our overall OR gate. Let's do OR X, and then we'll have our AND gates like this, and another AND gate making plenty of room. And then after the AND gates, we have Xnor, and then Xnor again, and then 1, 2, 3, 4, A0, B0, A1, B1, and then we'll have our third Xnor gate like this, and then we're going to invert one of the inputs. So here's A0 inverted, and then B0, and then we'll say A1, B1. And so you could then expand the Xnor gates into ANDs, ORs, and inverters, etc. if you wanted to. But the point is, you have an upper and a lower converter that do each their separate task, and then we OR at the end. Moving on to exercise 3, it says generate the logic gates that convert 4-bit binary to 4-bit gray code and show that it works with a timing diagram. Now, let's remind ourselves how we convert binary to gray. So in either direction, gray to binary, binary to gray, we copy the MSB. And then to convert binary to gray, we add this bit and that bit, so 0 plus 1 is actually 1. And we would ignore any carries, and so 1 plus 0 is 1 again, and then 0 plus 1 is 1. So this is the number 5 in binary, and this is 5 in gray. So the pattern looks like copy the MSB, then add across, then copy, then add across, then copy, then add across. And so we would ignore any carries. Once again, let's try a simpler example, 0011 to demonstrate the carry. That is the number 3 in binary. And so we would copy the MSB, that 0, add 0 to 0, copy 0, add 0 to 1, copy, that's 1, and add 1 to 1, that's actually 2, or 10, but we ignore the carry. So 2 would be 10, but the 1 there is a carry. And so this is 3 in gray, so how do you count to 3 in binary? Is that 0? We have 1, 2, and then 3. But notice when you go from 0 to 1 to 2, so in going from 1 to 2, 2 bits have to change, and that's not the desirable thing for counting in gray code. So instead, we have 0000, 0001, O O. I said 1, but I wrote 0. Um, O O O 1 O O 1 1 and then O O 1 O. That's in gray code. And so this is our representation of the number 3 in gray code, and that's what we get over here. So the key is we're adding successive bits. So how do you, let's start with the MSB over here, and we'll just make a wire that copies it across. But then we have to add it to the next most significant bit, which let's just call C. And so I'll take this and make a wire over here, and then take my wire and feed that into our most basic form of an adder, which is an Xnor gate. And so then this will be the MSB of the gray, and then this will be, I'll call it C prime. And then for our next most significant bit, we have to add C and B. So C will come over here, we'll add that to an XOR, and B gets fed in like that. And so then that's B prime. And then our least significant bit I'll call A. And so we have to take B and add it to A. So here's our A prime, and so A has to come over like that. And so now we've just used a series of XOR gates to add successive bits, but we have to copy the MSB unchanged. And so our timing diagram could be, here's, A, B, C, MSB. What I'm looking for is, let's just say 0, and then all of a sudden we have a 1, and then let's just do the example we did earlier of 3. So A and B are both high at the same time, and then we have 0 and 0. And so what you should have then for A prime, B prime, C prime, and MSB, which will be the same, is MSB is easy. It's going to be always, we're copying it across. And then C, if C is 0 and then MSB is 0, those are equal, and so the XOR would be low, and so C prime is low the whole time. And then if you have a 1 1 here, that's 3, and so 3 in gray code, it would look like this. So the what produces the A bar output? Well, we would have A, but then B would also be high at the same time, and that keeps the XOR gate low there, and so A prime would be low the whole time. So that's how you do the circuit for a gray code conversion. Now we move on to question 4. Once again, we're in section 1, chapter 6, combinational logic. And this is the topic of parity checking within the general topic of error detection in bit streams. So one way that you can have a single bit error and detect it is to see that the parity of the whole stream changes. So consider the circuit on the right-hand side. We're being asked to produce the timing diagram, but what exactly is that going on there? So if you have an XOR gate, that's making sure that the bits here are different. And so these would be true, both true, so you'd have 1 1, but then the XOR would say false there. And so so notice that you have some number of ones, so 1 and 1, so there's an even number of ones and you get a 0. But if we change even 1 bit, then let's say that's a 1 there, then that's still a 1, but then the 1 1 in the lower XOR gate makes a 0 here, and that becomes a 1. And so this is true for an odd number of ones. So we can actually generate the truth table for this whole circuit, and we should do that. So there are 4 inputs, A, B, C, and D, and X. And so let's try to enumerate can do the first 8 here and then the first 8 somewhere else. So we'll just draw 3 more lines like this. Now we can do our truth table. So here's 01, 01, 01, 01. So that's 1, 2, 3, 4, 1, 2, 3, 4. So this is the first 8 of 16 possible states. So we'll say 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. And in this case, A is 0 the whole time. So let's say further that this is C and D, and this is B and A. Now, if you have A is false all the time, just the XOR truth table, if you have just 2 inputs and like that, 01, 01, 00, 11, these are the true states like that for XOR. But if A is 0 the whole time, you're just up here in this combination here. So B is equal to X. So what you can really surmise is that in this lower XOR gate, it's just going to be B. B will pass through. This will be B right there because A will be low for these first 8 states. So we have essentially C XOR D, and then that XORed with B. So this first state C XOR D would fail because they're equal, and so 0 XOR 0 would produce a failure there. But then if you have C XOR D, that would produce a 1, and then that's different from this 0, so there'd be a 1 there. Then keep going, so C D XOR makes a 1, and then that's different from this 0 over here, so again we have a 1. Now there's 2 1s, and so C XOR D is 0, and that's the same as the 0 of B, and so we have a fail there. And then C XOR D 0, 0, that's a 1, that's a 0 because they're identical, but then that's XORed with B, which is now 1, so that's actually a success. And then if we keep going, C XOR D 0, 1, that's a true, but then we have 1 XORed with a B, which is 1, and so that produces a false. Finally, next to finally, we have C XOR D 1, 0, which produces a true, and that's true. That true is XORed with another true, and so that's false. And then C XOR D 1 XOR 1 is 0, which is different from the B there, so we actually get a true hit as well. So there's precisely 1, 2, 3, 4 trues, and then there's 1, 2, 3, 4 falses. So the point is, this is true only when there's an odd number of 1s. So if you have 0, 0, 0, 1, that's an odd number of 1s. That's true. Here's 3 1s, and that's true as well. So the parity output here, this is true if odd number of 1s. So I could have repeated the analysis with A being true. That would just produce the same results, only the 4 true states and the 4 false states would be rearranged. And in fact, I could have easily called this, A and B, or I could have said B and A, and that it doesn't matter how in what order you do things, as long as you recognize that if um, you have a constant as one of your inputs for XOR, then that means that either your other input is either like B equals B, or B gets changed to B bar, depending on what the state of the input is. So the point is, so you have to pay attention to that, but this P output just ends up being true if there are an odd number of 1s. So to produce the timing diagram, which is the goal of part A, So the first bit time, that's 1011, so I think we should have a 1 there. And I'll just do the bit stream and then draw the timing diagram at the end. So there's a 1011. So this parity would be 1, and then we have 0, 1, 1, 0, even 0, 1, 1, 0, 0. And so that again is a 0, 1, 1, 0, 0. There's no change there, so it's a 0. 0, 1, 1, 1, so that's a 1. 1, 0, 1, 1, 1 again, 0, 0, 1, 1, back to 0, and then 0, 0, 0, 0 for a 0. So our timing diagram shows the first bit time goes up, 1, 2, 3, high for 2, low for 2, like that. So that's the timing diagram of this parity output. But then there's a more intricate assignment in part B, which is to develop a symbol for the 4-bit, 4 parallel bit parity checker, and connect 4 of them to a 4-to-1 multiplexer with 2 data select lines. So let's draw that design. But the key here is the skill, if you can call it a skill, is it's kind of like um, the way we draw things. We can encapsulate this, we'll call it parity checker, and then it has 1 output and 4 inputs, and then we need 4 of them going into a 4-to-1 multiplexer with 2 data select. So what we'll do is have our multiplexer like this, and then we'll need 4 inputs, 2, 3, 4. How many data select lines will we need? I think we'll need 2 data select lines. So here we'll call, actually I'll call these S for select, and this is the data. And then we'll have, let's say, PC1, oops, PC, actually let's make these a little larger, so I'll just do PC1, and then PC2, PC3, connect in, PC4 will connect there, and then we'll have our 2 data select lines, and then there should be 1 output. So this is our 4 to 1 multiplexer. And so all this parity checking just changes to 1 data line. Devise a simple timing diagram that align the data select lines with parity check outputs. So I think what you want to do is cycle the data select line, so just each PC gets checked equally often. If you favored one combo of select bits over the others, then I think that would be it would reduce the likelihood of catching an error in any of these bit streams. So for our data select, I think we want to have our LSB oscillating at this frequency. There's 4 possibilities, so 1, 2, 3, 4. Well, so we have 0, 1, 2, 3. So I guess I'm cycling twice. So 0, 1, 2, 3. And then my other data select line should be 0, 0, 1, 1, 0, 0, 1, 1. So 0, 0, 1, 1, 0, 0, 1, 1. But then what that will mean is if So now we should think about bit times. And so the first bit time I'm checking the first uh, parity checker, and the second bit time I'm checking the second parity checker, and the third bit time I'm checking the third, you know, parity checker. So I think it's more appropriate. We can make a simple timing diagram where each of these are just constants. And so if I just said 0 0 0 0, how about where's PC2? I'll put for the data 1 1. PC3 will get 0 1 0 0, and then how about PC4 is 1 1 1 0. So just some constants that I'm sticking into the parity checkers. Um, but then, for my first bit time, I'm checking the first parity checker. All right, so then that should be a 0. In fact, I'm going to make a little number line right here to make sure my stuff stays lined up. Um, so 1, 2, 3, 4, 5, 6, 7. So just so you can see that bit time corresponds to the first bin, and so on and so forth. So in my first, this is 1, 2, 3, 4, 5, 6, 7, 8-bit times. That's 0, 0 for my data select. That's going to be checking PC1, and so my value, my result for the multiplexer should be 0 there. Because if you check the parity of all O's, you should get 0. There's no, the sum of all ones is an even number, 0. Okay, so then in my second bit time, my data select picks PC2, and then there's 1 and 1. So again, that's a 0 because there's not an odd number of ones. My third bit time, here's my third bit time, 1 0. Now we're looking at PC3. There is an odd number of ones there. My fourth bit time is here, and I'm looking at now PC4, and there is an odd number of ones there, so it's 1 like that. So this pattern would repeat because I've got these parity checks. I'm feeding in constants to them, so I would have 0, 0, 1, 1, 0, 0, 1, 1, like that. So that's our analysis of the parity checker, and also including the idea of a multiplexer as well. And now we move on to section 2, chapter 7, latches, flip-flops, and timers. And the problem reads, consider figure 2, part A. If the clock signal frequency is 20 megahertz, what is the period? So remember that if we want the period of any clock frequency, we have to invert that frequency to obtain the period. So this is 1 over 20 megahertz. 1 over megahertz is a microsecond, so that's a 20th of a microsecond. And the period, a microsecond is 1,000 nanoseconds, so that's 1,000 over 20 nanoseconds. Tens cancel, 100 over 2 is 50. So period is 50 nanoseconds. So the answer to part A is 50 nanoseconds. Now, if the delay through the inverter is 5 nanoseconds, what inverter, by the way? Well, specifically, we're talking about the pulse transition detector. And so the pulse transition detector is important because it's what triggers the D flip-flop on the positive rising edge of the clock signal. So sometimes we indicate the positive edge like this with a little arrow. And so the pulse transition detector is responsible for the positive edge triggering. And so if this delay could be a few nanoseconds through that inverter, when fed into a NAND gate, when they're high both at the same time, then the NAND gate produces a low, then we invert that to get a high signal. But that produces a very narrow high signal, much narrower relative to the original clock period. So this question is not complicated. If the delay through the inverter is 5 nanoseconds, what's the width of the pulse coming from the pulse transition detector? And the answer is 5 nanoseconds. So this should be 5 nanoseconds wide, because that's the time in which both of these signals are high at the same time. And so you can think of popping these bubbles, and that just becomes an AND gate, so it's high whenever both signals are high at the same time. And that's only uh, normally it would be 0 if the delay there was no delay in the inverter. Um, but in fact, it's not the case. So 5 nanoseconds would be the pulse width out of the pulse transition detector. But then the third question is, what is the duty cycle relative to the clock signal? So the whole point of having the pulse transition detector is to change the clock signal to a tiny duty cycle pulse, because it should be small compared to the width of the clock pulse, or the period of the clock pulse. So this would be the period, because here would be the next positive edge. Let's draw a better picture. Here's the clock signal. It's low. There's a transition up, down, up again. So from positive edge to positive edge, that's the period, and that is our 50 nanosecond period, right? So what happens with the 5 nanosecond delay into the pulse transition detector is that we get a pulse that is 5 nanoseconds wide, and then we would get another 5 nanosecond wide pulse, et cetera, et cetera. So we're changing the duty cycle. So the pulse width here would be 25 nanoseconds. It's just a 50% duty cycle relative to the whole period of 50 nanoseconds. But now we have a 5 nanosecond width compared to that 50 nanosecond period. And so what was a 50% duty cycle has now become a 10% duty cycle. 5 divided by 50 is 10%. So the pulse transition detector changes the duty cycle from 50% to 10%. So the next question is, produce a timing diagram of the digital or the D flip-flop with the following bit stream input. Each new bit is associated with a clock pulse. So that's not difficult. We're going to get uh, a high and then a low, 1, 2, 3, high, then a low, 1, 2, 3. But the key here is that, so it's just the same bit stream, but how do you draw the clock? So the clock is like this, right? So that's one transition, and that causes the bit 1 to be loaded, and then the next transition causes the next bit to be loaded, and so on and so on. Hope I get this right. Boom, there's another positive edge, and then another positive edge. My thing is competing with me. So I'll just draw like this. So that positive edge there triggers the next 1 to be loaded, and then the very next positive edge triggers the next 0 to be loaded, so we get 0. So the point is, this D flip-flop flips and flops on positive clock edges. So now we move on to the second problem for Chapter 7, Latches, Flip-Flops, and Timers. And so we're looking at a JK flip-flop in permanent toggle mode, so high is connected to J and K simultaneously, and then the positive edge of clock is the one that triggers flips and flops. So the clock frequency is 40 megahertz. With what frequency does the Q output oscillate? Well, let's keep in mind, if we do that same timing diagram as before from the last problem, remembering that this is a device which is toggling on every positive edge. Well, some of the edges are positive and some of them are negative, are falling edges. So if there's the clock, then this JK flip-flop will, let's say, toggle to 0, and then toggle to 1, and then toggle to 0, then toggle to 1 again, and then toggle to 0. So if you count the number of rising edges, 1, 2, 3, 4, and you count the number of rising edges for the Q output, this is 1, 2, this is Q, this is clock. So it looks like it's a half the frequency. And so if we start with 40 megahertz, that's for the clock signal, with what frequency does the Q output oscillate? That should be 20 megahertz. And so there is a relative divide by 2 operation between the positive edge of clock and the positive edge of Q. And so the third question, or the second question, is using the same principle, construct a circuit with JK flip-flops that changes the clock frequency from 40 to 10 megahertz. So building off of what we currently have, let's take our Q and bring it down here. Don't worry about Q bar for the time being. Let's just have another JK flip-flop. And then we'll have that be triggered on positive edge. And then what if I connect my high output here? So I'm always going to have this toggle J and then K. And this is my clock in, and here's my Q output. So I want this to always toggle, but it's only going to be triggered to toggle on Q, and this is my, let's say this is Q0 and Q1. So let's start with the clock. 1, 2 positive edges, 3 positive edges, 4 positive edges, 5, 6, 7, 8. I'll put a little arrow on each of my positive edges. Now this one is going to cause, let's say they both start initially cleared, but then the first positive edge will cause uh, the first JK flip-flop to rise, fall, rise, fall, rise, fall, rise, fall. But then these positive edges are going to trigger the second JK flip-flop to rise and then fall and then rise and then fall. So how many positive edges? Well, here there's 8 and then 4 and then 2. So 8 down to 2, that's a factor of 4 in frequency. So there are 8 rising edges in the bottom here, but only 2 rising edges in the top signal. So this is Q1. This middle signal is Q0. So there's a half the frequency, and then the fourth of the frequency is the top timing diagram. And so if this clock frequency is at 40 megahertz, then the top one will be at a factor of 4 lower at 10 megahertz. So in this way, you can have uh, the clock, be divided, and I'm sure there's other ways to do it, but this makes sense to me that we're just using the occurrence of positive edges, and the positive edge of this Q will then become the trigger for the next toggling flip-flop. Moving on to section 3, chapters 8 and 9, shift registers and counters. The question is, for this 4-bit bidirectional shift register, design a timing diagram and serial input for serial data inline that causes a single bit to enter the register and then bounce from right to left repeatedly. What is the frequency and duty cycle of Q3? So this data shift line, this right-left shift, if you see the so if you see the a high signal on serial data in and right is high, then gate 1 will be those two things ANDed. And so whatever serial data in is, it'll pass to this OR gate and then become the data bit of the first flip-flop. And so if I keep my right signal high, this right signal comes across, and for the second gate, it attaches here, here, and here. So actually, these 4 gates correspond to loading, uh, the bit as if it's starting on the left. So the serial data in goes through gate 1 and ends up in D1, and it becomes the output of Q0, which then is fed, from left to right to the next D flip-flop. But if the right-left shift line is active low, then these gates are used. So the right-hand gates of all the pairs. And so the serial in line, if this is low, G1 would be blocked, and serial in would go all the way through that top line, all the way to G8. And then uh, where would the next data bit come from in this flip-flop? We have to follow the trail. So it would come through G7. And so this D output here, actually, sorry, not G7, this D output would go like this and would come through, yeah, G7 there, and then this data output would come here, connect to that dot, and go through G6, and then these squares would loop. So this D output goes up there, connects all the way back to G5, and so this is actually from right to left shifting. So our job is not to build this or reinvent the wheel, but we just need to devise the timing diagram. So I want my serial data in on bit time 1 to be high, and then let's just say low for 3 other bit times. So there's 1, 2, 3. Let's see, how am I going to draw this the best, most clear way? I think it's best if I start with making a number line like that. 1, 2, 3. I want my serial data in to be like that, and then low, 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 low. So you get a 1, 0, 0, 0. And then that's the first few bit times, and that's going to be my serial in. And then for my right left shift, I want it to be high. And in fact, I want it to be high. I need to make, again, another number line. So like that. Yeah. And so I want it to go high and remain high. So 1, 2, 3, 4. Now, if you shift 4 times, you'd think that it would fall off the table. What does falling off the table mean? Well, if it's here and then, where does it go next? Well, this output technically would have it connect back to the gate to the left, but if it were right shifting, then nothing would happen, and so the bit would just stay there. Um, but then where would you get your next bit? I think your next bit would be 0, and so then eventually the data would just disappear, and we can think of this as a table, where if you're pushing something off and then suddenly it falls, then it's gone. So we actually had a homework problem similar to that. But we need to have at least, the first bit time needs to get the data bit 1 in here. We'll have 0, 0, 0. And so our right left shift, that looks like RI. This is L bar. So I should say, um, I'll just call it right shift like that. So I need to be high for 4 times. The first one is just to get serial in into D1, and then the next clock will get that 1 to the next the D flip flop. So that's where it starts, but then continuing from there, so you can think of this as load and then shift, shift, shift. So 3 shifts. So 1, 2, 3. Now I've got my 1 over here on the 4th bit time. And so I've got 1, 0, 0, 0 like that, and suddenly my right left shift signal needs to drop. And so, but remember the 1 is already there, and so if I drop it for 1, 2, 3 bit times, this is going to be awkward. Let's see. If I drop it for 1, 2, 3 bit times and then raise it again, this 1 will shift once, twice, 3 times here, and then I need to make 3 rightward shifts, so 1, 2, 3, and then left. So I think the pattern is initially there's this kind of setup phase, and then it should look like this. So if I say I want my right shift 1, 2, 3, 4, and then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is right, 2, 3, 4, and then left, 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 right, 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 left, 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 right, right, right. And then um, what will happen is, let's just treat this case as a special case. But in general, there we go. So the if I just look at Q3, it's 0 here, and then 0, 0, 1, and then 0, 0. So let's just track. If the 1 hops there, 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 now my 1 is there on this last rightward shift. If I shift it left, now it's over here. Shift it left again, now it's over here. Shift it left a third time, now it's over there. And then shift right, right, right. On that third rightward shift, you get the 1 back at Q3. 3 left shifts, 1, 2, 3. That's 0, 0, 0. And then on the third rightward shift, you get a 1. You get the 1 back in here. So the 1 is just bouncing back and forth. Okay. But look at this signal now, because the question is, what's the frequency and duty cycle of Q3? Um, well, I didn't really say what the clock frequency is, but you get the period here is there's 1, 2, 3, 4, 5, 6 bit times go by before the 1 returns, and so let's call that the period. And so you can say 6, bit times, and then the duty cycle would be 1/6. So this is what it would look like here. So technically, yeah, so here's the signal. The period is from there to there. And so you have 1, and then 1, 2, 3, 4, 5 zeros, and then 1 again, so that's where it recycles. So there's 1, 2, 3, 4, 5, 6. So the width, whatever the width is 1 bit time, and then the total is 6 bits. And so the duty cycle is, I guess, 100 over 6%. So what's ever 100 divided by 6, it's like 16 something. Let's see. Yeah, 16.7%. So the point is, in the analysis of this, we have to get the bit in there, and as soon as we get the bit in there, then we can just assume that every 6 bit times that the bit will show up at Q3. So you could imagine connecting LEDs and making the light appear to bounce back and forth, and then you could expand this to having, many rows of lights, and then you could scan them back and forth. So then you could, draw a message, like, for example, park here, or slow ahead, and make a traffic sign this way. Finally, for the second problem of third section, chapters 8 and 9, shift registers and counters, we consider figure 5, which shows a 16-state counter with enable and clear functions. The waveforms are applied to the count, enable, clear, and clock inputs as indicated. Show the counter output waveforms in proper relation to these outputs, but remember the clear input is asynchronous. So we'll argue that actually although we could count up to from 0 to 15, actually only the Q0 and Q1 outputs are ever activated. So clear is active low, so in this first portion here, nothing can happen. And also the count enable has to be high for the counting to take place. And so remember that the clear input is asynchronous, so as long as we're in a high state for the active low clear here, then we're good to go. But the count enable has to be also high, so let's block off this time here and this time. So on this first, and remember this is a positive edge triggering device, so the first positive edge is there, second positive edge. So we get two positive edges, and so along will come our Q0. On the first positive edge, it will go high, and then on the second positive edge, it will go low, and then nothing happens after that because we're outside the enabled window. And then on our, for this is our Q0, so for our Q1, we'll have Q1. So we would get on that first positive edge, we would get nothing because we're starting at 0 0, and then we would get 1. So this would be, that's like saying 0 and then 1. Remember the MSB is on the bottom here. And then the second positive edge there, this one would go high, and then there'd be no third positive edge because we're outside the enabled window, and so then uh, the the clear function comes along and clears both of those. So the what happens next is we have to go all the way to the next enabled window. So let's go down here like this, and we'll go down like that. And so we get again 1, 2 positive edges, and remember this is cleared. So we're starting back at 0 and 0. But at this first positive edge, our Q0 will go up and then down on that second positive edge and go like this. And then our Q1 line will become high like that and continue on so that the final state should be 1, 0, or 2. So we should get 0, 1, 0, 0 for the final state. So we have to pay attention to, is the clock, or is the counter enabled, and then how many positive edges are we getting? Because of this symbol, we need positive edge triggering for it to advance the counter, and then we would have wound up in some interesting state, but then of course the clear signal, it sets it to 0, and so we start counting again. All right, so this has been the study guide for midterm 2, and so please use these solutions after you have to check your work, of course, but then hopefully this has been a good preparation for the take-home midterm for the course.